I've got a GTX 1660 Super, 6 gigabytes of VRAM. That's a $150 graphics card. And I'm running an 8 billion parameter AI model on it. Locally, no internet, no subscription. In this video, I'll show you exactly what happens inside that GPU when you do this, why it almost doesn't work, and how it works anyway. Before we talk about GPUs and memory, let's answer a more basic question. What actually is a parameter? Picture an AI model as a machine full of tiny knobs. Each knob is just a number. When the model is untrained, those knobs are basically set randomly, turn on, and you get gibberish. Training is the process of slowly adjusting each of those knobs by showing the model billions of examples of text and nudging the knobs bit by bit until the output starts making sense. That's genuinely what training an AI means at a physical level, tuning knobs until the machine's output gets better. Once training is done, those knob positions are frozen. They're the model. When you download Quin 38B, you're downloading 8 billion of these tuned knob positions. Every one of them plays a small part in why the model predicts good text instead of noise. Here's the problem. Every one of those 8 billion knob numbers has to physically sit somewhere in memory, so the GPU can use it during calculation. If we store each number at full precision, 16 bits, or 2 bytes, 8 billion of them needs about 16 gigabytes of memory. My GPU has 6. On paper, this should be impossible. This is where quantization comes in. Instead of storing every knob value at full precision, we round it, compress it, using far fewer bits per number. Go down to 4-bit precision, and those same 8 billion knobs now take up roughly a quarter of the space, around 4 to 5 gigabytes. Each individual knob does lose a tiny bit of precision, but with 8 billion of them working together, that small loss barely shows up in the final output. This one trick is the entire reason consumer GPUs can run large models at all. So how does actual text turn into something these billions of knobs can work with? First, your sentence gets broken into small chunks called tokens, not always whole words. Each of these token pieces then gets converted into its own list of numbers, called an embedding. Here's the intuitive part. These numbers aren't random. They're positioned so that similar meaning tokens end up numerically close together. Pizza and burger land near each other in this number space. Pizza and car land far apart. The model isn't storing dictionary definitions. It's storing position in a giant map of meaning. Now here's the core trick running inside every transformer layer on your GPU, called attention. Take this sentence. The trophy didn't fit in the suitcase because it was too big. What does it refer to, the trophy or the suitcase? You instantly know it's the trophy, but the model has to figure that out mathematically. Attention is the mechanism that lets every token look at every other token in the sentence, using those number lists from a moment ago, and decide how much weight to give each one. Through this process, the token for it ends up mathematically pulling in information from trophy, because that's what actually explains the sentence. Stack this across many layers, and the model builds real understanding of context, not just isolated words. And running millions of these look at every other word calculations at once is exactly the kind of massive parallel math GPUs are built for. That's the real reason AI needs a GPU in the first place. Not just more power, but a completely different kind of math happening all at once. Once all of that processing happens, the model predicts a single next token. That new token gets added to the conversation and fed back in, and the entire process, tokenizing, embedding, attention, prediction, runs again for the next token. One token at a time. That's why longer responses take longer to generate. The model is redoing this whole loop for every single word piece it produces. Here's the part most people don't know. That 6 gigabytes isn't just holding the model. It shares space with something called the KV cache, the model's memory of everything said earlier in the conversation. The longer your chat gets, the bigger this cache grows. That's why a short prompt runs fine, but a long conversation can slow down or even crash. You're running out of the same memory the model needs to keep thinking. If a model genuinely doesn't fit, tools like Alma can offload some layers to your regular CPU and system RAM instead of the GPU. It still works, but CPU math is dramatically slower than GPU math. So you end up partly GPU accelerated, partly crawling on the CPU. That's why some setups technically run, but feel painfully slow. So here's the full picture. Billions of tuned knobs, compressed down through quantization so they fit in memory. Your words turned into numbers positioned by meaning. Those numbers constantly checking each other through attention, one token predicted at a time, sharing memory with the conversation's own history, and falling back to the CPU when it runs out of room. If you're running local AI on a budget GPU like mine, the takeaway is simple. Pick a quantization level that fits comfortably in your VRAM. Keep an eye on how long your conversations get, and don't be surprised when things slow down near the edge of your memory limit.